Howdy. Today we're prepping for mass and weight. Start off with a little bit of a warm up question, then watch a little bit of a microgravity video as as the beginning part of our class and discussion, and then do a lab. You'll have a worksheet for the lab. The worksheet looks like this, and that's a physical worksheet. You can write along as I write on it. Um, this video, I think I'm gonna change that video anyway. That's an old video. I don't know, whatever. Then we'll go over some graphs. After that, this video will end. Um, I'm gonna do the lab on this video. Uh, so that's what I'm gonna do on the video, and then the video will end, and then you'll have a an ed puzzle on Veritasium. Derek from Veritasium um, talks about the difference between mass and weight. And then you'll have to do a Sparky quiz. And here we go. Um, let's see. Mr. Morrison, the warm-up question for today. Mr. Morrison has a mass of 75 kilograms. How much does he weigh? So a lot of people would think, okay, well, I weigh 75 kilograms. That's the way you speak in the world of, um, you know, I oftentimes say physics muggles, like Harry Potter, we have muggles, non-magic folk. In science, though, mass is actually kilograms, and weight is actually measured in newtons, which you're going to find out in a little bit. So, how much would I weigh in space? Well, that's part of the discussion. We would have a conversation about that if I was in class. Um, but hopefully, that I have no weight in space. Would I, though, have mass in space? So that's part of the main concept. We're trying to differentiate between what is weight and what is mass and how are they different. So although I would have no weight in space, like if there was a scale, me and the scale would be floating around in space and I couldn't stand on the scale and get a reading, but I still would have mass. Like if you were to move me around, it'd be a lot easier to move me around in space. Um, but if I have a mass here, 1 kilogram, I I can feel the weight going down. But in space, I wouldn't feel any weight, but I would be able to feel if I was trying to push it around, I would be able to feel some resistance. Like it's going to say, okay, I know you want me to go that way, but I'm going to resist it. And that's Newton's laws, really. And in this unit is Newton's laws. An object at rest stays at rest. And so even if it's in space at rest, if you try to move it, it's going to resist that motion. Let's see. On the moon. So on the moon, what happens to my mass? Well, the kilograms actually in the world of physics, which is why physics is so good at doing things mathematically, scientifically, is the kilograms remain the same on the moon and in space. But the gravity changes. Your gravity is dependent upon where you are. Are you on a planet? Are you on the moon? And then I hope you would know that you could jump much higher on the moon and you would weigh much less on the moon because it has much less gravity, about 1.6 is the gravity factor on the moon, whereas 9.8 on the Earth is much stronger. If I had a 75 kilogram bag in space, let's say instead of one of these, I had 75 of these in a bag. That'd be as heavy as me. I'm 75 kilograms, so imagine just lugging around a bag of me. That sounds like I'm like a dead body in a bag, but just 75 kilograms in a bag and lugging it around on Earth would be pretty hard. It'd actually be a lot easier to move me around out in space, but I still would provide resistance. And the bigger the bag or the bigger the object, the more resistance. I mean, think about it. Isn't the Earth just a giant ball floating in space? Right? So the bigger the ball gets, the harder it is to move. And if a ball was as big as the Earth, you would think it was solid and not moving. But isn't the Earth also being pulled? Isn't it moving? So wow, mind blown. Yeah, it's moving around the sun. The sun's a much bigger ball. So don't get too wrapped up in that. Just know that the mass of an object is fundamental and gravity changes. Okay, that's kind of the big thing for today. I'd like to see if this works. If this doesn't work, you'll have no audio. I'll hear the audio, but you won't. This is Branson microgravity, and I can. That's not gonna. Hard to-
In a spaceship with lots of other wonderful.
Too hard to really see what's going on.
5,
I can't.
3, 2, 1, release.
Okay, so we should be back here, and this should work. Hopefully, you got the audio.
5, 3, 2, 1, release, release, release.
Fire, fire.
This is Branson, very rich guy from Sturgeon, Atlanta, and he's taking some people out into near Earth orbit, just barely on the edge, and he's going to give them the opportunity to experience weightlessness for just a small amount of time. So this rocket is going to be sitting there, kind of coming up. The upper reaches the atmosphere, and it's going to.
Welcome to witnesses. You're clear to unstrap.
Okay, so this is microgravity. There still is gravity there.
Welcome to space.
It's just
To
that
all
they're
you kids down there, I was once a child with a dream, looking up to the stars. Now I'm an adult in a spaceship with lots of other wonderful adults looking down to our beautiful, beautiful Earth. To the next generation of dreamers, if we can do this, just imagine what you can do.
they're all falling at the same time,
Oh my God.
including the plane. But it's falling around the Earth,
Oh my God.
and so you feel weightlessness. If you step on a scale, I mean, how would you step on a scale? You couldn't. So they're digging on this. They're having a good old time.
My God. Oh, this is unbelievable. This is too unbelievable.
Your plane would have to go much higher in order to experience this, and then your plane would also have to like dive. This is not permanent though. They're not in a permanent orbit, so they're going to drop out of orbit now. And once you drop out of orbit, you've got to take controls of the plane. And once you take controls of the plane, then you'll start to feel the experience of gravity, because you're not just going to go all the way down and land, crash land on Earth, right?
And please return to your seats and strap in. Approach and re-entry.
Okay.
Get back up.
But yeah, once they take over controls of the plane and bring it back into Earth, they're going to have to, make it act like a normal plane where you do feel gravity. If you didn't feel gravity, you'd be diving straight down and crashing. So you may have felt weightlessness on a roller coaster because you dive down, right? But that's only for a moment because you're going down. So pretty neat little video there. Okay, so hopefully that picked up. Okay, next we got a lab, and so the lab is about weights, and so let me get that started then. Okay, so the lab itself, where did it go? There it is, right there. Okay, so we have a force sensor right here, and a force sensor is ability. It has a hook, and it has the ability to see how much something weighs, just like a spring scale. So if I took this weight and I put it on a spring scale, I could read the side, and it would tell me how heavy this object is, right? The heavier the object, the more the spring goes down, right? And so that's basically a spring scale. And the same thing is this is really a wireless spring scale that's going to give the information to the computer. So a couple things about this. It just starts off with what is the point of a zero button? Well, this is just for your lab. We just got to make sure that when you're weighing something that you want to have it zeroed. Think about this like if you were going to go to the grocery store and buy apples. Do you want to measure the apples or do you want to measure the tray with apples in it, right? So let's say I had a box and that box had apples in it, right? I could weigh the box and I could push 0, and then that would mean it would kind of like cancel out the weight of the box, and then I put apples in, and they only pay for the apples. So that's the point of the 0 button. Okay, so now it says what happens when you pull on the hook and what happens when you push on the hook. So if you look here, I'm going to pull, I'm going to push, I'm going to pull, I'm going to push, I'm going to pull, I'm going to push. And I hope you can see that what's going on there is when I pull, the number's negative. And when I push, the number's positive. And the reason that is because when I set it up like this, I'm pulling down, and down is negative. I've got nothing on here, but it says there's 5 newtons on there. That's not true. I'm going to 0 this because I want it 0 just like that. And that is zeroed. This is just, that's kind of dumb. It's basically giving me way too many, digits. So 7 times 10 to the negative 15 or is basically saying 0.0000000000007 newtons. So there's nothing on here. Maybe if I could hold really still, it would actually go to 0. No, I can't do it. Anyway, that's 0. So let's not worry about that. Okay. Then it says, what's the standard of physics unit for mass? Well, this is a kilogram, right? But what is a kilogram, right? So if you see in the picture, I'm not sure how hard this is to see, but you see in the picture, you've got a liter of water. This is an old picture. It says Obama 08. That's an old picture. A liter of water actually has a mass of 1 kilogram, which is really kind of cool because how much water would this 1 kilogram be equivalent? 1 liter. And if you had 2 liters, what would it weigh? Or what would the mass be? 2 kilograms. So that's actually pretty cool. You know, and every single weight increment is exactly precisely what it is as compared to an equal measure of water, right? Now, a liter itself is a cubic decimeter. And a cubic decimeter is that idea where you have 10 by 10 by 10. It's a cubic decimeter, which means a 10 by 10 by 10 cube. And I actually have one somewhere over in the other part of the room. I'm going to go grab it real quick. Nope, I couldn't find it. So anyway, I must have moved it during the summer, and now I don't know where it is. But anyways, you get the idea. It's like, that big of a block of water. Water is usually in a little jug, so you don't normally see it in a block, but that's 1 kilogram. Okay, so now with that in mind, we're going to go to the next page. And, how do you convert from grams to kilograms? That's pretty important because this is 1 gram. Sorry, this is 1 kilogram, but it's 1,000 grams. And so this is 100 grams. So what is that? It's 0.1 kilogram. So if you have grams, you take the decimal and you go backwards 1, 2, 3 places. And I'll show you how to do that in a moment. Okay, now to the lab. The lab is actually on the next page. I can turn that off because I'm going to the next page. Here I am. And so what you do here is you'll take some weights and you'll take it and you'll put it on. And then you'll try to keep a sample. And it's going to put a point on here as soon as you put the kilograms. So the kilograms here is this little one. I said is 0.1. So I'll get to that in a second. So 0.1 kilogram, enter. And I see a point show up there. And so what we're going to do right now is we are going to plot that. If I can do this on here, am I going to be able to do this with here? So the mass in grams is, come on, give it to me. Where is my pencil? I'm going to pause this and find my pencil. Okay. So in grams, that was, and I have to write too big, but that was 100 grams. And the way we get that to kilograms is we move the decimal over 3 places. I've moved the decimal over 3 places. I get 0.1. I mean, if you want to, you could say 0.100, but it's the same thing, kilograms. The zeros and the and here just say how accurate you want to be. Okay, it says times 0.98 for the force in newtons. Now, we measured it, and 0.98 is kind of cheating a little bit, but we did measure it. If you look on the other one, it said 0.97, which is close to what you would get if you did it mathematically. So I don't care. Put 0.97, 0.98. 0.98 is fine. And this is the force in newtons, which is capital N newtons. And I'm just going to do 2 more, right? And so I'm going to get another one, and this one is actually 50. And so I'm going to hang it like this. I'm going to do 150, right? And so I'll do this one, and that'll be 150 grams. And so that will be 0.15 kilograms. And I don't know if it's going to erase it if I go back to the page. What's going to happen? Maybe it'll be there when I get back. I don't know. And so I'm going to do the same thing here. I'm going to weigh this or mass this, and then I'm going to keep a sample. 1.4, and what I got here, I got to put the number in here, was 0.15. 0.15. Hopefully it's there. It's not there. I got to click in there. 0.15. Enter, and it gives me a second point, and I'm starting to get a little slope here, right? And I'll do one more real quickly. Let's see what happens. I'll put in just 200 by itself. 150, 200. So last one, 200. Actually, I'll do 2 more. I'll do 200. Keep sample. Go in here. 0.2. Enter. Give me my third point. Now I do 1 more point. I'm going to do the big boy here. Ooh. Keep sample. And then 1 kilogram. Enter. Ooh, look at that one. It's a big one. Ooh. All right. Let's see if I go back to the other page. Oh, it's still there. Look at that. How about that? Okay. So, so you get all those numbers, but anyways, let's see if it's still writing. I don't remember what that one was. It was like around 1.4 something, 1.49 newtons, something like that. And then I'm going to go, I'm just going to go to the big one, which is 1,000 grams. And that is 1 kilogram. Guess what that is? That's 9.8 newtons. Does that 9.8 sound familiar? Well, that 9.8 should sound familiar because we're talking gravity, right? 9.8, right? Times 1 is 9.8. I'm not done with the lab, though. Okay, then what we're going to do is down here, we are going to try to get a slope. And so it's so small in this thing. I wish I could zoom in on that so we could get a better idea about what's going on. But linear, it's a line. So if I do this and I click there and I come back here, it should give that to me. It does. Man, that's small. Man, that's small. Let me grab my glasses. You'll never be able to see that. I mean, put on a giant screen or something. Let me grab my glasses. Oh my goodness, it says negative 0.982. Wow, I did a good job. Negative, the slope is negative 0.982. So, okay. So going back here, don't need that most of the time. Now what we're going to do is I'm going to move down this page. And if I move down the page, I think what's going to happen? It's drawing. I've got to get back to my other tool. Okay, there we go. Move down the page. Okay, so then we had a couple dots, right? So we had a dot. There's the pen. We had a dot about there, and a dot about there, and a dot about there, and then we had a dot way down here somewhere, and it went like this, right? And so what do we have in this graph? Well, we had a slope, and the slope was equal to negative 9.8. But negative 9.8 what? Negative 9.8 what, right? So let's look at this. In this thing, we have on this side, we have mass on one side and we have force on the other. We have mass on one side and force on the other. So now we look here and we have mass, and mass is measured in kilograms. And we have force, and force is measured in capital N newtons. It's the name of somebody, so you got to have it capital. So if it's rise over run, right? Slope is rise over run. Then what are the units? It's whatever it goes up, which is newtons, over whatever it goes across, which is kilograms. So newtons per kilogram. And we're almost there. And then we got to kind of finish off the notes on this page. So what does this tell us? What this tells us is it tells us in our notes that if we take a y equals mx plus b equation, right, we start off with y equals mx plus b, then we can make our next great equation in the world of physics. So y is our vertical, and our vertical is force, which is measured in newtons. And m is our slope. I'll get back to the slope in a second. X is our horizontal, and our horizontal was mass. And be careful with that, because you know how these letters, y equals mx plus b, m in that sense is slope, but m in our sense is mass, plus b. And so what's b going to be? Well, if you look back up, the b is the y-intercept, which is 0. So that point right there is 0, which it very often is 0, right? And so this case it is as well. It's 0. And now, unless I didn't zero my force sensor, if I didn't zero my force sensor, then it wouldn't be 0. It would be something other than 0, which would be a good lesson actually to see what happens if you don't zero the force sensor. So looking back at this, what actually is that? And I think you know what that is. What is that negative 9.8? I mean, what is that negative 9.8? Well, that negative 9.8 is equal to something we know as gravity, of course. And gravity is usually denoted as an A. So sometimes you might say just G for gravity, or you could say A and maybe put a little g here to let people know that you mean the acceleration of gravity, right? So the equation that we have then becomes, it's a lot of clicking to go back and forth here. The equation that we have here becomes the force is equal to gravity times mass. Now we usually write it like this. The force, which we know is weight, is equal to the mass of an object times the gravity of the place that you're at, right? And that actually changes. Where are we here? Well, we're on Earth, right? So that is what it looks like if we're on Earth. But what would it look like if we were somewhere else, right? So what would it look like if we were somewhere else? So if I go back to here and I look at this G graph, this gravity graphs, I get a sample of pretty much what we just did. This is on Earth, and it's saying, okay, what would it look like? And oh, by the way, I did it positive here instead of negative. Maybe I should have done it negative. But I mean, when you usually do mass in weight, a lot of times we do it positive. That's the only thing different, right? That slope right there, that blue slope, is a slope of 9.8. Why? Because this is exactly what we have. We have an apple, which weighs about a kilogram. It's a big apple, by the way. A gallon of water, which is 3.8 kilograms. And my soap, which is 75 kilograms. And I plotted that out, and I get the slope, which gives us this equation. The force of gravity on Earth equals mass times the gravity on Earth. The force of gravity on the moon would be times the gravity on the moon. But it's always times the mass. And so force of gravity is measured in newtons, mass is measured in kilograms, and gravity can either be measured in, so this is something you probably know, gravity can be measured in, where's my pen, there it is, in newtons per kilogram or meters per second squared. It kind of depends on what you're asking. If you're asking how hard is gravity pulling down, then it's newtons per kilogram. But if you're asking if I let go, what will happen, then it's meters per second squared. They're 100% related. I hope you know that the weight of something is related to the acceleration as it falls. So lastly, what about different places? And so I got to get rid of that again. So now we're going to go to different places in the, well, that's weird. It left it there. I'm going to get rid of that. They're all gone. I think they're all gone now. Okay, so this is comparing 100 pounds on the moon, only 16 pounds. Remember I said it was like 10 to 1.6. On Mars, you would only weigh 100 pounds, would only weigh 38 pounds. But on Jupiter, 100 pounds would weigh 253 pounds. And so you get these curves here where Earth is the blue one, right? And then the moon is the bottom one in red, and Mars is the orange one, and then Jupiter is the green one right there. And so you could do the exact same experiments, with the exact same things, an apple, a gallon of water, and Mr. Morrison. You would see I'd weigh 735 newtons on Earth, but I'd weigh 277 on Mars, and I'd weigh 1,875 newtons on Jupiter. However, my mass wouldn't change. My mass is the same everywhere I go. Okay, we're almost done with this. No, maybe it seems like it's taken a long time, but here are the completed notes. And the completed notes are here. And you've already pretty much done it, but I want to show you the stuff at the end. Okay, so there's some samples right there. There's what we did there. Here's Mr. Morrison example. How much would I weigh? Force of gravity is weight in physics, not mass. So how much would I weigh? Well, I'm 75 kilograms. I times it by. The negative is just saying down, so we don't really need the negative in all cases, but just be careful, the negative, like always. Times 9.8. Now I times it by 10, right? I was being lazy. Right? No, I didn't times it by 10. I wasn't being lazy. I times it by 9.8. I thought it was 750. Anyway, then the weight is in newtons. So in physics, we weigh in newtons. On Earth, we're still like pounds, but in physics, we say newtons. And then we have our summary. And the summary says, what is mass? There's three things for the summary. What is mass? And it says that mass is the amount of matter in an object measured in kilograms, and it's constant, which means it is the same everywhere. What is weight? Weight is the force of gravity on an object, or the force of gravity on a mass. It's measured in newtons, and it changes based upon your location: Earth, outer space, moon. And then finally, we have Newton's first law. And Newton's first law is the law of inertia. And that says that any mass has a resistance to a change of state of motion. So you don't need weight to resist motion. You need mass to change the state of motion. Remember I said we're out in space, even though this mass has weight on Earth and it has no weight in space, that it still would resist motion in space. It'd be easier to move, that's for sure. Take the largest football player at Rockland High School and grab him by the shoulders and try to move him on Earth. It'd be pretty difficult to move him on Earth. But if you're out in space and you try to move him, you'd kind of both go back and forth, right? But he would be a lot easier to move if you were in space than he would be on Earth, because that weight kind of anchors you, like you've heard of an anchor, anchors you to the ground. And that's really it. These three things, 1, 2, 3, they are going to be associated with test questions. The test question will ask you this. It will say, explain the difference between mass and weight. And you're going to give me 6 things. You're going to say that mass is the same it's constant. It's the same everywhere. It's measured in kilograms, and it's the amount of matter in an object. That's probably not the right order. It's the amount of matter in an object. It's measured in kilograms, and it's the same everywhere. That's 3 for mass, and you give me 3 more for weight. Weight is the force of gravity on an object or on a mass. It's measured in newtons, and it changes depending on location. That's 6 questions on the test. That's literally 6 points. And a lot of you guys will bomb that question. I'm telling you what it is right now. I'm telling you in your notes. You might want to put a star in your notes and say, this is on the test. 6 points. A lot of you guys will get 4 points on it, or maybe 3 points on it, but you're not remembering it, even though I'm going to remind you, because you're not committed to getting that question on the test. I'm just telling you, that's a question that a lot of people get wrong. Okay. Last thing is there is a Veritasium video to watch, which is going to be an Ed puzzle. And then there's a Sparky quiz to do, which is Sparky Quiz 2.1. And hopefully the video, this video helps you to understand it. And hope you have a great day. And I will see you next week. Ta-ta!